Hey, Melissa,
Yes, Jam.
have you ever been 5 years old?
Yeah, just once. I guess one time, 365 days.
Have you ever listened to somebody explain something and wish that it was simpler?
Yes, all the time. That's my number one grievance with most of the things I have to do for my job.
It seems like there's a lot of people who feel that way about chemistry.
Mm-hmm.
So they take to Reddit, where many people go when they have feelings, and they ask people to explain things, in this case, chemistry things, to them as if they were 5 years old.
Yes. r/explain like I'm 5.
Exactly. So you already knew about this. That's crazy that you already knew.
I love that. I love that website.
So today we have for our Q&R a lot of Explain Like I'm 5s.
Great.
Where hopefully you will explain to all of us like we are 5.
Okay, that's my goal. I don't regularly hang out with a 5-year-old. I do regularly hang out with a 6-year-old.
There you go. Okay.
So I'll try to explain it to him like I would to him.
Okay. Got it. Nice. Okay, that's good.
All right.
So you have a real person of around the age that we are trying to all be.
Yeah.
Okay, good. Sounds good. Should we do it?
Let's do it.
All right.
Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
Bonus edition.
As if you were 5.
Yeah. Reddit explain like I'm 5 edition.
Yeah. It's like, what if I had been on my toes enough to be like, the podcast that helps you understand the chemistry of your everyday life if you were a 5-year-old.
I would have loved that.
So there are a lot of questions here ranging from why isn't water flammable to how writing on a steamy mirror works, which honestly, that is something that my own not quite 5-year-old son has wondered about, the steamy mirror thing. Yep.
Okay, great.
So are you ready for the first one?
Yes. Yeah, let's do it.
Okay. This is, these are all on that subreddit, Explain Like I'm 5. This is from Front Illustrator 654. Can someone explain why water isn't flammable even though it has hydrogen in it? Chemistry is a hard subject for me. I have never understood molecules and chemical bonds and such. This isn't for any assignment. I'm just genuinely curious.
Okay. Well, that's a tall order to explain everything, but I guess I would say that flammable things are things that give energy to fire. And once a fire is started, it just kind of like when you push a ball down a hill, how it just keeps rolling. The flammable is like, okay, we can push the ball down the hill, sort of. That's what flammable things do.
Okay.
And they asked like, okay, well, why isn't water flammable even though it has hydrogen? Hydrogen gas is very flammable.
Right.
And I would say that hydrogen gas is 2 hydrogen atoms bonded together, and a bond is essentially sharing electrons. So if you imagine one atom has an electron, another atom has an electron, that's not enough. They need more than just one electron. And so they'll come together and share that one electron between each other, and then everybody has enough electrons. Now a good example of this is dual income, no kids. Is me, my husband, we got married, we both have income. I don't have as much income as I would like. And he doesn't have other resources that he would like. We can share our resources together, and we were better off financially after we got married. I definitely wasn't. And he is better off in other ways, after we got married. So you share these resources. That's basically what atoms do. They form relationships by sharing electrons.
Got it.
Okay. That's not, I guess, saying double income, no kids. That's probably wasn't a good 5-year-old thing, but, whoops.
All right.
Maybe I'm just explaining it to you like you don't, like you're maybe a college student.
Yeah.
That's who I'm used to explaining things to. Okay, so when that happens, though, you can have a whole new substance if you share electrons with different things. So 2 hydrogen atoms sharing their electrons becomes hydrogen gas. A sodium metal not sharing its electrons is explosive. That same sodium, if it shares its electrons with chlorine, then it becomes table salt.
Right.
Or if it takes electrons, I guess, from chlorine. Shares. If it shares, it's with chlorine. So there's different ways that different atoms can share their electrons, and then they take on basically whole new identities. Kind of another good example is like, when you have a friend that makes you better and like brings you towards positive things and encourages you into and then you have those like toxic friends. Sort of like that with atoms. If they're sharing their electrons with the wrong person or the wrong other atom, they can become explosive. It could be bad. If they share their electrons with something good that brings them stability, that's another option.
I see. Yeah.
So when the hydrogen shares its electrons with oxygen, now we get this whole new substance. And it's just that substance, the water, it can't work as fuel. It doesn't burn up in the same way that other things can burn up to spark that reaction. It's not the right gas in the car, you'd say, so that it can't really run this reaction.
I see. Okay. Interesting. So Wawa, like no fi-fi.
Wawa, no fi-fi, because, well, it's really, the question is like, why is water not on fire?
Yeah.
Is it because hydrogen gas can be on fire? Why can't water? It's like, well, they're just two totally different things.
Yeah.
That's like asking why a weeping willow has long leaves and an oak is like tall. It's like they're just different.
Yeah.
They're just totally different.
Yeah.
It doesn't have the thing that it needs to have to catch on fire.
Right. Interesting.
So there you go.
Not a question I had thought of, but then once you go to like the hydrogen gas is flammable, and I can see where,
Hopefully that helps you understand and like chemistry a little bit better. That's all I'm trying to do.
This next one is from user EXYNTH. Don't know how to spell that. Exynth, maybe? Or pronounce that?
Yeah.
How does carbonation work? Where do the bubbles come from for so long?
That is a great question. Okay. I'll say kind of two things about carbonation. Is one, if you have a liquid and you pump gas into it, the gas can dissolve in the liquid, which means every individual CO2 atom, which is carbonation is carbon dioxide, will be surrounded by whatever the liquid is. So that's dissolved, as if it's completely surrounded by the liquid. It's dissolved. So we can pump that gas in there and then it will get dissolved. And they have to these atoms have to bump into each other and start to find each other. And enough of them have to come together that you'll start to see a visible space where we have a bunch of gas bubbles instead of the liquid. And then they have to get large enough that they're so lightweight that they're basically able to overcome the amount of energy or the force that's pushing down on them. So that's one place that it's coming from. But also, there's usually carbonic acid in a lot of sodas, for example. And when you mix CO2 and water, they will it's basically doing a chemical reaction where the carbon dioxide and water are turning into this acid, and then it'll like break back up, and it sort of goes back and forth like that. But there's sort of a principle in chemistry where, like, say you're making water, as you're evaporating that water off, more water will be generated. So it'll sort of favor the side or make more of the side that is currently missing. So if we have this carbonic acid and it can break up into water and CO2, and the CO2 bubbles are floating away, then the chemical equilibrium is like, oh, well, we need more CO2. So it'll try to, then more of the carbonic acid will break up into CO2 and then it'll go away. And so there's like two sources of carbon dioxide that can hide in your drink.
Interesting. And we have thought about that in a longer episode.
The one about Mentos.
Yeah. And
right?
well, didn't we just have one about carbonation? Why does carbonated water taste?
Yeah, why does it have a taste?
Yeah. So it's like we kind of hit it from different angles, I guess, but very interesting. This next one's from Fresh Air Inspector. Pretty much verbatim question from my 9-year-old daughter. So explain like I'm 9, I guess. You get a little bit more sort of years to work with here. I just lost it. Oh, here it is. If everything is made out of atoms, then are atoms different colors? In other words, how do colors get attached to things? What are colors made of?
Okay, this is a great question. I would say that colors aren't because of atoms, but they're because of electrons. So every atom is made up of electrons, protons, and neutrons. And the electrons are like the outermost layer, and they do the most things. So like I said, they can be shared to make bonds, but they also can absorb energy and put out energy. And they can do that in different amounts that are like very particular to every single atom and molecule. And my favorite example of this is like if you have a 5-year-old and they eat a snack and then they have a lot of energy and they run and let it all off. That's similar to what electrons are doing constantly. They're taking in energy and then they're letting out energy. But some of them just happen to take in the energy and in the right wave area. I don't know how to say it, in the right amount that it is visible to us. So we have lots of episodes about that. But essentially, I would say everything is made out of atoms. But the atoms aren't necessarily different colors. It's the arrangement of atoms together and when those molecules to make molecules, and when those molecules are made, their electrons are interacting with light in ways that we can sometimes see as colors. And sometimes you can't see it. Sometimes it's UV. And so we've talked about how there's a type of clear plastic that looks clear to us, but it completely blocks UV light.
Oh, right. Yeah.
And a lot of seeing glasses are made out of that.
Uh-huh.
And so like if you could see UV, it would just look black to you. It would look solid, but it's clear to us, you know?
Yeah.
So I don't know. I don't hang out with 9-year-olds, but hopefully that was a good enough explanation for 9. It's just about the way that the electrons interact with the light.
It does also seem like anytime our episodes have touched on any color and light related stuff, that the hard thing is it is hard to wrap our minds around no matter how old or young we are.
Yeah, that one I think is just challenging. But I do think that it could be beneficial as any of our episodes about color kind of touch on that.
When cooking, are you ready for that one?
I did have this written out nicely. Let me think about this. Let me say it like this: is the energy can be absorbed in big amounts or small amounts. And big amounts of energy are usually invisible to us, and small amounts of energy are usually invisible to us. But if you get like sort of right in the middle, that's where visible light, like that's where we can see color.
Yeah.
That's where it's visible to us. It's like, so it just has to be absorbed in just the right amount for us to be able to see. And that's when colors get attached to it, as the 9-year-old said. Sorry. Okay. I liked that way of writing it out better.
That's good. That's good. Okay, this next one's from Anonymous Quark. When cooking food, what decides if something melts, burns, or solidifies? Example, when we fry an egg, it turns into a solid. When we fry a block of butter, it melts. When we fry a slice of toast, it burns slightly. In school, we were told that heating substances always turns a solid into a liquid or a liquid into a gas, but obviously this is not always true. So what decides if something melts, burns, or solidifies?
Okay, I actually feel like this is kind of two separate questions or two separate things I need to clarify. And one is, if you heat a block of one substance, like if you have carbon dioxide or water or whatever, that pure thing will typically go from solid to liquid to gas when held at constant pressure. So foods, though, are not one pure substance. Everything that you're cooking is a lot of different things. So it's a complex array of a bunch of other things. And a lot of them have often even been cooked before. So when we're cooking, we're not just heating something, which results in a physical change, which is what solid to liquid to gas is, where it's the same molecules and then they're like spreading apart further and further to go from solid to liquid to gas. That's what heating those things are. So heating a block of one substance, we're not mixing it with other things. It's not doing chemical reactions. It's just adding more energy to something that already exists so that it can have enough energy to move around, basically. But when you're cooking, you're doing so much more than that. So what determines what happens when cooking is what are the things that you're putting into what environment. So, and then are they going to be able to have chemical reactions with one another? So, for example, you said when we fry an egg, it turns into a solid. We actually have a whole episode about that.
Yeah.
But essentially, these heat will allow proteins to denature and then bond to one another. So it's not like we're just heating one individual protein. It's a variety of proteins that spread out and then do not exactly chemical reactions, but they are interacting molecularly to start to stick together. Whereas when you are toasting something, for example, when we fry toast, it doesn't always burn. Actually, that initial brown thing that forms is a Maillard reaction is what we call. So it basically, that brown stuff on toast, what makes toast toasty, is a very big chemical reaction that's happened. And it's like made a huge long chemical that covers the whole top of your toast, which we call a polymer. It's a big molecule that's made up of a bunch of small molecules that have reacted with each other. And so what decides what happens when you cook something is if it melts, burns, or solidifies is essentially like, what is that thing and what chemical reactions is it doing?
Oh, yeah. That's good.
So, yeah.
What is that thing? Yeah.
Yeah. What is it? It's because it's usually not, butter is actually usually just like fat and it's solid. So when you heat it up, it's doing the same thing that water does when you heat it up. Because I think butter is often like, it's not just fat, I guess, but it's more of a consistent of like mainly one thing. Whereas like eggs or meat is like a bunch of different proteins and fats. And so there's like way more that can happen there.
Yeah. It's like that one's abiding by the rules the most. Like what he's saying we're taught in school. It's like, butter's doing what we're taught.
Yeah. Because it's like mostly a fat.
Yeah. It's like kind of, one thing. But it's like, well, bread that you're toasting or eggs that you're cooking, it's like a lot more going on.
There's a lot more. Yeah, because bread is like has protein, it has carbohydrates, it has like a lot of times you put butter on it, so there's fat that's going into play with it. So it's
and it already went under its own crazy process to even become bread in the first place, and then it's a slice you are putting in a toaster or whatever.
Yes. Yeah.
So it's like, man, crazy. I think you did a good job with that. That was hard. There's a lot
Thank
there.
you.
It's like those are like literally every aspect of that. We've done like 4, 5, maybe even 6 episodes that connect to what he's asking about. So
so that's how much there is to talk about it. It's a lot. Yeah.
This next one's from Bellale. Do any calories get burned through the heat of cooking? If I made a batch of cookie dough that was 100 calories exactly, but it comes out of the oven, is it still exactly 100 calories?
I would say it depends on what the people who decided it was 100 calories did to measure that.
Right.
So 100 calories, I guess calories in general are just energy. And when you're trying to determine how much energy one thing can provide, you can do that by literally burning it and measuring to see how much energy does it put out. So like one that we'll use is we have like, if you burn something, how hot can it increase the temperature of water? So those are called calorimeters. So my question about your cookie dough is, did they measure that 100 calories when it was in the dough form or when it was in the baked form?
Right.
So if it was 100 calories exactly in the dough form, my guess is that it's probably slightly less when it comes out. Just because I think there's a potential that things are evaporating. So like an example that I have is like alcohol has a lot of calories in it, but if you put it in a pan, a lot of times a lot of the alcohol evaporates away.
Right.
And so you've lost some of the energy there.
Right. That's interesting. Because I feel like what may be evaporating in the case of a cookie might be the things that have no caloric.
Right.
Whatever, you know, like some water.
Yes, I don't. Yeah, that's what I'm wondering is like, would anything evaporate in a cookie? I don't know. But I could see it's like when you're heating it
Mm-hmm.
and these reactions are happening between the things, sort of going back to our last question, do those take energy or are they putting out energy?
Yeah.
So it's like because like chemical reactions are happening,
Mhm,
you know? So
mhm.
I'm like, I think I think that's a tricky question. And
Yeah.
I think the basic thing I could say is like, did they burn the dough or did they burn the cookie? And we could answer that experimentally by burning the dough and burning the cookie.
Right.
And like measuring the energy of both. But I don't feel like I have a good answer. Like for me, I'm
Yeah.
like, is there something that might evaporate from there? You know, like what's the smoke point of butter? Is that when it starts evaporating? I don't remember. You know, so it's like things like that you're like, are we losing anything in the oven?
Yeah.
Or is something changing to make it like where it would be less efficient energetically?
Uh-huh. Yeah, that's a good. I can see where maybe the longer you cook something, that yes, it would.
Yes.
But
So this is what I wrote in my overall conclusion is it's hard for me to see what in a cookie would evaporate off. And by putting more energy in, which is baking, I don't think you're reducing the energy unless that happened, you evaporated something, or unless you facilitated a reaction that somehow made it less, like made there be essentially less fuel, you know?
mhm.
But I don't know what that would be. But it's probably pretty close.
Yeah.
If anything, I think it'd be slightly less, but I think it's probably close.
Yeah. Interesting. Wow. Seems like a solid enough answer.
Thanks.
And
Thank
also
you.
probably gets them to where they close enough to where what they're trying to figure out. It's like
our friend.
if anything, it's like 99 calories. You know.
Yeah.
It's like maybe so minor, but it would be kind of crazy if you're the person wondering this to realize if it were true that the calories change a lot.
Yeah.
You know.
Yeah.
Like I see where the curiosity comes from.
Our friend Ryan B once asked me, your neighbor now too, used to be my roommate, once asked me about protein. Like when you cook food, does the protein go away? Because isn't the protein of the raw meat? And we had a similar thing where it's like, yeah, I mean, I think the protein can change form, but I don't think the basic nutrient content is going to probably change much.
Yeah.
It's tricky.
Yeah. Interesting. Last one from Own Monster 3000. If I draw something on a steamy bathroom mirror, why does the image reappear the next few times the mirror gets steamy? And my own almost 5-year-old has asked about this same thing.
Okay, so here's my thought. I've done no research on any of these. These are just all chemistry off the cuff. When you're writing on a bathroom mirror, you're initially doing two things, which is one, you're like knocking the water molecules off, right? So that's what makes the initial line of the steam is you're like removing the water molecules. They're not in the same pattern anymore. But you're also depositing your finger oils. And those are often clear. And so once all the water molecules go away and they dry, I bet you would still be able to see that writing even without it being steamy, but you just have to be at just the right angle to see it, you know?
Yeah.
But I'm guessing that residue of oil is left behind. And oil and water don't like to mix. So the water molecules would preferentially deposit other places.
Yeah. Huh.
So maybe, sorry, I didn't do that very good like a 5-year-old. So maybe if I was talking to a 5-year-old, so if I was talking to your son, I would say like, you know how sometimes your fingers feel like they have some coating on them? When you write on the mirror, you leave some of that coating behind and it's invisible, but it's still there.
Yeah.
And that coating repels water, which is why you don't just soak up water every time you take a shower. But it's also why the mirror doesn't soak up water the next time.
Right.
Depending on how much you've talked about body oil and lotion.
We haven't talked about that. I was trying to think about when we talked about this question last time about it appearing next time. I can't remember what I even tried to say, you know?
Yeah.
I certainly wasn't thinking about a podcast answer, for everybody. I probably was not trying to do a good job.
Yeah, you're probably like, just finish your bath.
Yeah.
It's bedtime, and we've been having these your son is one of the most curious kids I know. He's so curious.
Yeah.
So.
I was thinking too that sometimes whenever I've seen him or me or anybody write on a mirror that's steamed up, it also, it causes the water that is steamed up there to beat up and like form water spots that sometimes you can't really see very well. So I wonder if that's part of it too, where it's like, yeah, definitely your oils, but then because you can kind of see that after the steam goes away.
Yeah.
You can kind of see like, I can see like a little trail of
that's like
these larger droplets that kind of pulled together. Because I made them come together.
Yeah, like a water, like the water drops dry, it leaves something behind. Yeah. Mm-hmm.
That doesn't seem as likely as the oil thing, like you're saying. But I am like, well, you can see water spots afterward, and you've made it not be uniform.
That's what I'm thinking. It's about the uniformity. So even if it's the oil versus the water spots, I think the oil is more repelling, but the rest of your mirror has basically been in the same environment probably since the last time you cleaned it.
Yeah,
and so the water is like going to be equally attracted to everything except that one spot that you messed up.
Yep.
Yeah.
Yeah, that's for sure.
That's a good question.
Very good question.
That's a good chemistry of everyday life that we haven't talked about.
Mm-hmm. It's very everyday life.
We should do a version of this episode where it's just questions your son has asked you, and you just write them all down, and then you just ask me them.
That's a really good idea. There are definitely some he has asked that we've talked about. So it's like things we've already done, like leaves changing color. But it does have to require a pretty modified answer, But yeah, that's a really good one. I'll have to start making a note of those.
Yeah.
To be continued.
Okay.
I think that's all.
Great. Well, thanks for asking me questions, Jam.
Well, thank you for answering them, and thank you, Internet, for asking them out on the Reddit space.
Mm-hmm.
And if you have a question, a follow-up question, a question you would like explained, like you're 5 or like any age you prefer, please reach out to us on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts, ideas, questions with us. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can join our super cool Chem community of patrons on patreon.com/chemforyourlife. That's patreon.com/chemforyourlife. You get an ad-free feed of the show. You get some behind-the-scenes stuff. You get, depending on your tier you pick, you get some extra things, some thank you notes, some whatever you want to say, some coffee hour, exclusive hangs with Melissa and I, which we need to do again soon. But most importantly, you help keep the show going. Mm-hmm. We could not exist without you, and you keep it free for everybody else, which is, a really important thing for us. So, and a monthly exclusive bonus episode just for you.
Yeah.
Sorry. As I was going through, I'm like, what do I do again? Yeah, that's what we do. Anyway, we'd love to have you over at our Chem community. So go check it out, patreon.com/chemforyourlife. But if you cannot do that, that is okay, because you can still help us by subscribing on your favorite podcast app, rating, writing a review on Apple Podcasts or Spotify, and subscribing on YouTube and leaving a comment over there. Those things help us to share chemistry with even more people, help more people to discover the show and have the chemistry of their everyday life be explained to them.
And we want to thank everyone who is a part of our community. So thank you to Chris, Claire, Hunter, Katrina, Lynn, Scott, Steven, Timothy, Ash, Brian, Chelsea, Doreen, Elizabeth, Emily, Heather, John, Jesse, Latila, Rachel, Autoclave, Avishai, Chelsea, Sierra, Cullen, Emerson, Erica, Jacob, Jeanette, Julie, Christina, Suzanne, Venus, Vince, and Sarah. Thank you all so much for everything you do to make Chemistry for Your Life happen. This episode was created by myself, Melissa Collini, and him, Jam Robinson. And Jam Robinson is our audio producer.
And if you'd like to, nope, we don't have references for this one, do we?
Nope. So we just say thanks, Reddit, and yay, chemistry.
Yay, chemistry.